Good day, everyone. Welcome to this webinar on ocean best practices in future climate change. We'll just give people a few minutes to arrive before we get started.
So as people arriving, maybe I can mention to the people that if you have any questions for the presentations that you're going to see, you can put them in the Q&A. You should see it in the link under the Zoom, or you can put them in the chat if you cannot find the Q&A. After the presentations, we're going to have a discussion based on the presentations, but more generic on problems that they're associated with downscaling. And although you don't have access now to speak, if you raise your hand, if you want to discuss something with us, I will give you access and you will be able to discuss it with us. I will also put the link in the chat where we would like to invite you. There is a document there, and we'd like to invite you to share your thoughts about an idea that we have about the Global Coastal Ocean Model Intercomparison Program. So if you go to that link, you will see some questions that we would like. If you are able to share your thoughts with that will be very helpful for us.
Okay, let's just give it one more minute and then I'll get going and then other people can join. Let's go. Okay, that appears to have stabilized for a little while. So welcome everyone. Just to introduce myself, I'm Jason Holt from the National Oceanography Centre in the UK. I will just share my screen. There we go. Can you see that okay, Anna? Yeah, brilliant. Well, thanks. Okay, so welcome. This is a ocean best practices workshop on climate downscaling to the coastal ocean. So this comes out of the Future Coastal Ocean Climates Project, or FLAME. And so this project is part of the Coast Predict programme, and it's all endorsed by the UN Ocean Decade. So we're going to talk about climate downscaling to the coastal ocean. So we're in session 2 here. So we did another session yesterday morning in kind of the eastern time zones. I'll give a brief introduction to the downscaling question, the approaches, problems, and solutions, and then we have two case studies. We have Sarah Wakelin and Kyle Wells Gibbons, who will talk about 2 case studies, one in the Western Europe and one in the Arctic, and then we'll have a bit of a moderated discussion around the best practices of downscaling in shelf seas and coastal regions. Particularly the kind of questions we'll be thinking about, and I mean there may be other questions, is how do you see the benefits of a coordinated approach to global coastal ocean modelling? So, for example, a global coastal ocean modelling comparison programme. What opportunities and challenges would you see with that? How best to organise it? And how would you make it happen? I introduce these now, so maybe you can have a think about them as we go through the presentations. I'll put them up again at the end, so you don't have to remember them. So just to set the scene here, we're talking about producing actionable knowledge for future climate change impact in the coastal ocean, and this is because coastal communities and the blue economy generally require information about emerging and potential climate change and how to plan and adapt to that. And so this can be relevant to existing services, to coastal hazards, to blue economy, and the interrelationships between them. And generally, there's a big gap in the knowledge of what climate models can provide in this space because they're essentially not designed as coastal ocean impact models. So downscaling is the general approach to address this, but as you see on the right here, there's a very complex value chain from going from stakeholder interaction and co-designs through to actionable knowledge involving multiple different communities of practice. And so the question is, how can we better organize this? Because at the moment, this is done in quite an ad hoc, disorganized way. So can we better organize this to provide harmonized information in the coastal ocean around the world? And this would benefit, both the sectorial and cross-sectorial risk assessments. So how important and how strong a particular risks from a global perspective. It will build better process understanding, and importantly, it would help improve the capacity in underrepresented areas around the world. So this is actually a really significant problem, and particularly because of the questions of scale. So in climate modelling, we're very used to working at global scales, and maybe in high resolution global models, you might achieve something like a 25-kilometer resolution there. But as you go down to scales where humans interact in the coastal ocean, you need to kind of achieve things that are increasingly finer than that, maybe down to almost hundreds of meter scales. And it's not just scales; they're also increasing the different processes become more important as you get down to the finer scales. So, for example, the interaction with the land, things like tides. The interaction with the venting system becomes more important, and also single realizations into the future are not necessarily adequate. So you need to think about ensembles and multiple realizations of this. So there's been lots of work in the past on future coastal ocean downscaling. So these are examples on the right here from a paper by Mr. Encard in 2021, particularly focusing on living marine resources. And on the left of each of these, you see examples of global climate model parameters, and on the right, the corresponding downscaling with high resolution regional models. And in each case, there are qualitative differences between what you see in the regional model and the global climate picture. So you are adding kind of new value to the information with the downscaling process. And so at the top, we have primary production, so changes in sign in that. The middle temperature, so significantly reduced warming in the Yucatan Peninsula, for example, and then the bottom one changes in current sign in the currents to the east of Australia. Another thing to point out is whilst there's been a lot of work in this area, there's a great disparity in the regional coverage. So the map here is a meta-analysis, so simply counting numbers of papers in different regions around the sea, and you see there is largely focused in Europe, North America, and in East Asia, whereas some areas like East Coast of Africa and South America, for example, both have very few studies, if any. So this is the kind of thing we're aiming to address in the FLAME project. So just cycling through the approaches we can use here, the most obvious approach is more direct use of global climate models, but as is well known, these models typically have a resolution of about 1 degree. They require multi-centennial spin-ups, so they can drift quite far from present-day conditions, and that leads to biases which are really difficult to address. They're very expensive to run, so it's very difficult for people to do experiments with these, and they quite often have simplistic representations of things like marine ecosystems. So hence the need for downscaling. The most straightforward approach is to take a regional ocean model with or without biogeochemistry, so ROMS or NEMO or something like that, and force it both from the atmosphere and the ocean and run simulations with that. So this is a relatively straightforward approach. You can run multiple scenarios. It is generally compromised by the biases in the atmosphere and the ocean, but there are processes associated to correct that. So an alternative to that is you can actually run global models, so forced global ocean models. These can then use a much wider range of atmospheric forcing, so that they can use a high resolution forcing. So because they don't necessarily need the biogeochemical boundary conditions. They're comparatively cheap compared to the climate models, although when you start getting very high resolution oceans, they can become quite expensive. They do have a particular issue that they are no longer dynamically consistent between the ocean and the atmosphere, so you may get climatic drifts in these, for example. And you can go one stage further to that and downscale high resolution from those global forced models, forcing to high resolution in the coastal ocean. Then for addressing issues of atmospheric biases, then you can go to regional models like those from the Cordex project and use those for boundary conditions to downscale the atmosphere of the ocean at the same time. And then ideally you can introduce regional coupled systems, so regional systems models where you have an interactive coupling between the ocean and the atmosphere for your region. So these are pretty expensive and generally quite complicated to configure, but might be seen as an ideal case in this. So within Flame, we are beginning to coalesce on what we might call a global coastal ocean model and comparison project, so a GCO MIP, and potentially having 3 strands of activity with that, and each strand essentially an increasing practitioner commitment. So the strand 1 is relatively straightforward. It's about identifying traceable and reproducible simulations, so sharing common metadata, assessment approaches, diagnostics, and best practice. The second strand is then introducing standard model experiments, so specific collections of global climate model, a system model, and particular forcing scenarios within prescribed a common set of simulations and simulation strategies for these. And this can be conducted for any region and including global forced cases, which then can be used to provide boundary conditions for ecosystem models. So the third strand, which is possibly the more ambitious one, is actually to define some standard sets of regions, and these might well span particular shell sea types using typology approaches, so for example, Arctic models and tropical models, for example, or upwelling systems. So defining sets of example regions that cover the regional, the sub-regional, and the local scale, and then either look at existing simulations or new simulations that can provide multi-model realizations of each of these regions. So where next with this is there are multiple elements to develop here, and the idea coming forward for this is to have a set of protocol development workshops. These are most likely to be virtual. There may be some opportunities for some in-person ones, but they would cover aspects like the climate model downscaling protocols, the land sea coupling protocols, how we deal with very fine scales, so for example the coastal estuarine or the urban scale, look at ecosystem modeling, so for example what you do with missing data, the outputs targets, and then deciding that issue about the target regions and whether we can get some consensus on that. One possible opportunity to do this is the Coast Predict General Assembly is scheduled for this February, so we might see if we can have some sort of side event with it around that. Okay, that is all for me now. We'll probably park any questions on that to the discussion session. So now I'm going to stop sharing and we'll hand over to the first of our case study presentations, which is from Sarah Wakelin. So Sarah, the floor is yours.
Hey, Jason, I'll just share my screen. There you are. So thanks, Jason. So as Jason said, I'm Sarah Wakelin from the National Oceanography Centre, and I'm just going to share some thoughts about work that I've been doing on downscaling climate change to the Northwest European Shelf. I'm talking about a range of activities which have stemmed from a long-standing collaboration between the National Oceanography Centre and the Plymouth Marine Laboratory. So many thanks and acknowledgements to my co-authors. So yeah, so just to set the scene a little bit, the Northwest European Shelf, where is it? Yes, it's in the North Atlantic, with a strong connection to the Northeast Atlantic, and sort of right in the track of North Atlantic storms. It's in the region of shaded dark blue, really, in the red box there. Basically, water depths less than 200 meters. One of the important things is an exchange with the Baltic Sea, and in as many of these coastal regions and coastal seas, it's highly dependent on the rivers coming from land, fresh water and other things coming from the rivers. The whole area is a highly industrial region with high population densities, which has an impact on the ocean through things like wastewater discharge and industrial deposition into the ocean. So it's a well-used part of the ocean. And just an example of some of the services that we get from this particular area of the sea, it's an area of high productivity, high growth of phytoplankton, which leads it to be a hotspot for fishing industries. There's a lot of fishing that goes on there, and also aquaculture activities. There are a lot of extraction of energy, coal and gas rigs, and increasingly offshore renewable energy and sort of coastal renewable energy is also being extracted. The high production means that it's a region for uptake of carbon, so it can be important for the blue carbon sequestration. And also the general public also take a lot of pleasure from communing with the ocean, for using the ocean in various different ways. So like many of these regions, there's an awful lot going on here, and an awful lot of people really care about what's going to happen under the auspices of climate change. So just to introduce the modelling that we've been using, basically we've used a range of these Atlantic margin models at various different horizontal resolutions, from 12 kilometres to 7 kilometre resolution, and our current work is being undertaken at the relatively high 1.5 kilometre resolution. In the past, we've generally downscaled directly from the general circulation models in the absence of anything else, anything better to use. Where there has been intermediate higher resolution or with better processes, general circulation models, we've utilised those. But as a general rule, these are not suitable for informing your Baltic outflow, which, as you can see here, is very narrow strait. You need fairly high resolution, and I'll talk a bit more about that in a moment. So much of the coast has rivers. There's basically the whole coast has rivers. So these are the main river locations with the size of the symbol scale by the volume flux. So you can see there's also quite a lot of variability where the rivers are. We tend to use for the climate runs observation-based climatologies, but we're running into using model data sets now, and we typically perturb those by either precipitation or river flow from the driving models. For the biogeochemical models, they need other river forcing data around nutrients and oxygen and various other things, and they are even more problematic, as in what's going to happen in the future in climate change. So for the future trends, we either have no trend or some sort of a sensitivity experiment saying what would happen if there were, for instance, government policies saying that you had to reduce your nutrient flux to the ocean. Or there are, in fact, some model projections as to what could happen under various scenarios, which could be used. In the past, we've used past climatologies of atmospheric nutrient deposition as well, and also time series of the partial pressure of carbon dioxide in the carbon cycle models. So that's a general introduction into how we model the Northwest European Shelf. So I'm just going to run through a few results and some specific setups that we had. So this is one particular simulations that we did, downscaling under a business as usual a climate scenario from HydGem 2, a CMIP5 run. We were lucky enough here to have an intermediate hydrodynamic ecosystem model that we could nest within. We used a present-day climatology of observation rivers. We found at the time that we didn't have enough information about how these rivers' flows were going to change in the future, so the best bet was to just use the present information. And the same comments around the Baltic inflow. We didn't have enough information about what was going to happen with the Baltic, so we just kept it at present-day values. And this was a coupled physical biogeochemical simulation from 1980 to 2100. And the results here show a sort of very typical increase in I think these are possibly surface temperatures over the course of the century, of the order of 1 to 4 degrees across the continental shelf, and a freshening more strongly in the eastern North Sea here. So if you want to look at sort of diagnosing what's happening here, these are time series integrated over the various different regions of the Northwest European shelf. And we can see there are two basic things going on here. There's sort of the more coastal bound regions have a very consistent trend in the surface and bed temperatures sort of changing with time, whereas the more ocean exposed regions around the sort of northern North Sea and the shelf edge have a sort of very slow, to begin with, a very slow temperature rise, which then sort of builds around the middle of the century. So why does the Northwest European shelf sea freshen? And this is a schematic of what's accepted to be the flow around the North Sea. And you basically see a sort of inflow coming in from the Northern Atlantic of salty water coming onto the shelf into the North Sea and mixing with, I suppose, with river water, with Baltic inflow that's being released onto the shelf. And if we look at what happened in our model simulation, so on the left here is the recent past timescale, and the right is the end of the century. You can see that in these regions, the inflow onto into the North Sea has more or less stopped. And if we look at time series about what's happening here, so this is, if you just want to look at the blue line here, you can see a general collapse of the inflow, the Fair Isle Channel, the East Shetland current here, and the Western Norwegian Trench current, which is sort of positive. It's a northward flow into the southward flow into the North Sea in the present day, actually changes sign and becomes an outflow in the future. So we're not getting as much salty open ocean water onto the shelf, and this also impacts on the sort of shelf sections as well. So basically, we're not getting the salty water coming in to mix with the river water, and which is why the whole of the North Sea is freshening in this particular climate scenario. So we wanted to use this model to look at oxygen depletion. This is important for ecosystem health. And this basically shows a decline in the oxygen by the end of the century. We did some comparison with observations here and discovered that we had quite a good application to the seasonal cycle, but we had a bit of an offset. So it's kind of a bias correction, a downstream bias correction, in order to be able to compare our observations to our model results to a threshold and say that the oxygen depletion was more likely and more widespread for the future. And if we looked at time series, we saw a similar pattern here to what was happening in the temperature, with a constant trend sort of more on the shelf and with a sort of increasing trend in oxygen decline and the open ocean waters. So this led us to be able to diagnose the total decline into a solubility impact due to changes in salinity and temperature, and another one due to changes in the ecosystem. Yeah, so following on from that, we were James and Giovanni built and ran this ensemble of NEMO simulations from CMIP 5, RCP 8.5 models. There were 11 NEMO-only ones and 2 with the ecosystem URSEM switched on as well. For this case, we found that we felt we had enough information to perturb the river flows by future precipitation from the driving models. And again, these were transient simulations. There's opportunity here to improve the Baltic boundary conditions. So we perturbed the temperature and salinity by the changes due to that were seen in the global circulation models, and also introduced a sea surface height gradient from the Baltic to the open ocean from reanalysis. But this didn't change with time. So it's a better step than what we had before, but it still doesn't recognise any changes with the sea surface height with time and how I impact on the shelf circulation. So these are results from the ensemble about oxygen depletion. The top is the model that I showed you already. So we're seeing here oxygen concentrations in the past, change to the future, and the change to oxygen depletion. And it basically sets our initial results in the context of other results and gives us more confidence that actually there is going to be a decline in oxygen. It will sort of spread out in the future, even though the models don't necessarily agree on the magnitude of the change. So just very briefly, this of the 11 members of this is from Jason's paper, of the 11 members ensemble comparing the strength of the water column stratification with observations. And I think you can see from this the dotted line, the green dots is the observations. Some of the ensemble members do better than others. And so this can be a way of sort of improving your faith in the model and removing biases. Jason used this method to discount some of the ensemble members based on their present day climates. But even so, and this plot here is the fractional change in the summer strength of stratification in the models that were more believable, and you can still see there's a big range of response here. So I suppose where the models are agreeing, you get a confidence in your climate signal, and where they're not, you get a range of response of what the climate signal could be. And I suppose, and I should have said, I mean, these, just to reiterate, these are all under the same climate change scenario. So these are model differences coming in from the driving models. So I just wanted briefly to talk about what we're doing now in the Canary project. So we're looking at climate change in the Arctic and North Atlantic and impacts on the UK. So this is very exciting, hydrodynamic downscaling from a selection of a 40-member ocean atmosphere ensemble. I won't go into all of the details, but one of the most exciting things is we've got this intermediate North Atlantic and Arctic configuration at the 1/12 of a degree, which will run a more restricted ensemble. But for the first time, it will give us a consistent Atlantic and Baltic boundary. So we'll be able to see for the first time in a more consistent and believable way how the Atlantic and Baltic boundary conditions interact. So this time we're using model river data from the European Flood Awareness Scheme, and we will be perturbing them by the precipitation. And yeah, this is really the highest resolution that we've been doing for this. So work is beginning on this, and we'll be running climate models next year. So finally, I just wanted to say a bit about community engagement with the climate community. So we have this National Partnership for Ocean Prediction, which is an agreement or a cooperation between the Met Office, NOC, CFAS and PML and various other university departments. We're not completely exclusive. About building really UK engagement in all things to do with ocean prediction. Back in 2022, we had a workshop on the subject of seasonal to centennial timescales, so people who were involved in working on those timescales. And as a sort of test of the opinion of the community of people working on this, there was a general agreement that was a requirement for high resolution modelling of climate change and to look more at the sort of uncertainty, so really building into ensembles and model into comparison projects and really addressing the idea of uncertainty along the model chain. You've not only got the uncertainty in your climate scenario, but how that is interpreted by the global circulation model and then by your downscaling models as well. And there were calls for better funding and coordination, and thoughts about data and sharing, and I think a lot of these come under the flame ethos as well. And a lot of talk about translating what actually comes out of these models for stakeholders. With that in mind, as one of the MPOP activity groups, we've been trying to build and maintain a seasonal to centennial ocean community with a co-chair, Richard Renshaw at the Met Office. If anyone's interested in being involved in that, then please drop me an email. So finally, I'm not sure I managed to cover all this, but just to sort of summarise my basic thoughts on best practices for climate change. I didn't actually mention it, but a control or a hindcast simulation to compare your climate signal with helps with the interpretation of whether the climate change is sufficiently large to be believable in the context of the variability of your ocean model. Consistency of forcing is desirable, but if you haven't got consistency of forcible, then sometimes you just have to go with what you've got. Transient simulations are best. They helped us to diagnose what was happening with the oxygen and the salinity in the Northwest European shelf. I've used time slices in the past. They are useful too. Ensembles of model predictions really help for bias correction and also for gauging the probability of what's coming out of your model. Bias correction is good at all stages of downscaling. You can bias correct what's coming into your model, but also in your interpretation of the model, of what's coming out of your downscaled model. And I guess the final points about sensitivity studies. At the end of the day, we can't predict the future. We can only sort of say how the ocean responds with what we're putting into it, which is in the nature of a sensitivity study. So that was all I wanted to say. Thank you.
Brilliant. Thank you very much, Sarah. That was great. So I suggest we leave any questions for Sarah until the discussion session. So if you can unshare your screen, brilliant. And we can pass over to Daya in University of Alberta, Canada. So floor is yours, Daya.
Sure. I'll just share my screen. Okay, there we go. Hi, yeah, I'm Taya. I'm a PhD candidate here at the University of Alberta, and I'm going to be talking about some work that our group has done looking at high resolution studies in the Arctic and Hudson Bay, specifically focusing on the Canadian Arctic a little bit and different activities that we're working on. So as an overview, I'm going to talk about what we do with our ocean model and our biogeochemical modeling. And then I'm going to talk about some kind of more specific case studies looking at runoff, some of the CMIP downscaling and future prediction work we're doing, and as well as some of our really high resolution models that we're either developing or running. So as a bit of background, we run a regional ocean model for the Arctic and Northern Hemisphere Atlantic. This is what I'll call ANA throughout this. So I'm going to talk at first about ANA, which we run at a 1/4 degree resolution. So in the area of study, we're talking about resolutions on the scale of 8 to 15, 18 kilometers if we're looking in Hudson Bay and the Arctic here. This is the forced atmosphere ocean model coupled to sea ice and a biogeochemical model, which I'll talk about more in detail in a bit. And we specifically focus on the Arctic because this is a region which is very affected by climate change. It has seen as we move up in latitude, you see a higher rate of warming than at lower latitudes. and is very susceptible to these changes. And there's a lot of small communities which live in the Canadian Arctic and around Hudson Bay, which are at risk with these changes. So I'll talk a little bit about some of the work that we've done for that. So first, the biogeochemical model that we run with this was originally Bling, so that's on the left here. So this is a very simplified biogeochemical model. It's biogeochemical light, iron, nutrient, and gases. And you can see the schematic of how that works here on the left. However, this is a phosphate-based model, and the Arctic is nitrogen limited, not phosphate limited. So we have, and this was Inge de Scheppe's work for her PhD thesis. I have her email on the bottom there if you want to know more details about VIII. And so she coupled in a nitrogen-based model to our NEMO framework because these phosphate models were over-predicting productivity in the Arctic. So this is the biogeochemical ice incorporated model. And this is based on the Seibert et al. 2010 and 2011 original papers. So I'll show you, if it'll load. Here we go. So I'll show you some comparisons between this, and this is specifically for Hudson Bay here. So this is with the VIII is on the left in the top there, and then Bling is on the, oh, I'll just keep running that. It's kind of short. Bling is on the right, and then on the bottom we have comparisons with the MODIS Aqua satellite data. So with the satellite data, we can see that the chlorophyll A shows this similar melt and freeze pattern. The white area is basically showing sea ice. There's some delays in the models compared with the satellite data, but they show a very similar seasonal pattern. And the chlorophyll A concentrations emerge as the ice melts. So there's a bloom along the sea ice edge. So we can see that Bling over-predicts this melt compared with VIII, except in the autumn freeze up. So we see a much better representation with VIII than we do with Bling when we move into these nitrogen-based models. Okay. There we go. The other thing, another project which we've been working on, which I'll talk about, is combining hydrological model output for river data with our ocean model simulations. So this is, so the Arctic is again also very impacted by rivers as much as Sarah was talking about for the North Seas. We see the similar thing in the Arctic. Has a huge catchment region. It takes around 11% of the world river runoff, and a lot of global ocean models will use climatological data, which don't necessarily incorporate all of the smaller rivers or the recent changes that we've seen in Arctic rivers here. So we've looked at using output from the VIII hydrological model. This is the catchment regions and the dams that are simulated, which makes a big difference, especially in the Hudson Bay region, which is a heavily dammed region. And we can see the comparison if we look at the runoff and just the interannual variability between it that we can get with the VIII model compared with Diane Trenberth. This is the 2007 Diane Trenberth, which is really commonly used to force global ocean models. And we can see not only do we get this variability after 2007, but we see a much higher amount of runoff and a broader range. The other thing that we can do with hydrological model output, which is important in the Arctic, is we can include river water temperatures. So this is something which is not readily available in all data sets, but with the hydrological models, they include river water temperature output. So we can include this as a heat flux in our ocean model simulations. So this is just showing the heat flux that we see from these different coastal regions. They are just obviously coming in the Kara Seas. This is where the Ob and the Yangtze River drain into, which are the largest rivers in the Arctic. So it gives us the largest heat flux. And if you look at then on the right here, I have a map of the average change in the fall sea ice thickness when you include this river water temperature compared with the twin run where you don't include it. And we can see, so you can kind of see on the shelf seas, on the shelf regions here, we get this decrease in the sea ice thickness. It's on the range of 5 to 20 centimeters, depending where you are. It's a little bit higher near the Mackenzie and on the Canadian shelf here. And then you get this increase in the sea ice thickness actually out of our gateway straits especially down here in the Lincoln Seas and Nares Strait, as you go up through the coast of Greenland. And this is because as we've added this heat flux into the rivers, you end up you increase the sea ice mobility as you decrease the thickness along the shelves, which allows more export of sea ice. So there's a lot of knockdown effects that happen when you include this information. And so we found it quite important in our simulations, and this is an advantage of using hydrological model output to force this. The other project, which I'll talk about, is looking at, so this here is the Taulertuip-Amanga Marine Conservation Area. So this is this yellow box here, and this includes Jones Sound and the community of Grise Fjord, which we've worked with before on different projects. And this is, we're looking at how we can simulate the future oceanographic conditions in this region for the communities, for the community of Grise Fjord. And so we're looking at running future simulations for them using our model to look at coastal erosion and flooding risks. So the way that we're doing that is we're looking at using WaveWatch 3 coupled with our NEMO Ocean model. So so there's two parts to this, which is the WaveWatch 3 validation runs. These are run to present day, 2002 to 2003, using that same ANA domain that I showed you before with reanalysis data. So then we can compare this with satellite data and other observational products to validate and tune the model. And then we look at doing future projections with WaveWatch 3. So running from 2002 to 2100, forcing with CMIP6 GCM output. So for this, we've done some work on how we select the GCMs that we use for this and some bias correction strategies. So there's two parts to this. So on the left here, we have the anomalies in the region of temperature and precipitation from the 11 different CMIP6 models that we considered. So you can see the highest anomalies in temperature and precipitation are up here, come from UK ESM, and then we have lower anomalies on this side here. And then on the other side,
Sorry, Jason, I think we lost connection with Tahia. Can you see? Can you see
Yeah, I
here?
think she may have frozen, which is a big shame because it's been very, very interesting.
Yeah, we can give it a minute to see if she will be able to return. But this is a very interesting slide that we can use to
yeah, so we can,
have discussions too.
yeah. Okay. Okay, so she has dropped off the call. Okay, maybe she will reconnect in a minute. I wonder whether we should possibly proceed to some discussion points. So
Yeah, so first I was wondering, I cannot see any questions from the audience, but please, if you have any questions from Sarah's presentations, please put it in the Q&A and chat. Oh, Tahia is back.
oh yeah.
Hello.
hi, I don't know what happened or when I dropped.
We lost you for a minute there, but it was getting really interesting. So do you want to reshare this slide and keep going? Yeah.
Yeah, sounds good. Is this where I was when I dropped?
That's exactly right. Yeah. Yeah.
Okay, perfect. Yeah. Okay, I'll go back through this because I don't know when I lost you. Because I saw you freeze and then I was like, oh, I'm gone. Okay. So this is for our for looking at the marine conservation area up in the Canadian Arctic here and how we selected the GCMs that we used for the future simulations. So we looked at two things for this. We looked at the anomalies between the future to present. So this is in the temperature and precipitation. So seeing what models, because we want to have a large spread of possible future scenarios, and as well looking at the bias in the model in present day, in these models in present day compared with reanalysis data. So this is here, we can see these are high anomalies and these would be low anomalies. And then this is the bias compared with the reanalysis data. So from this, we ended up picking 3 different GCMs to use in this case. So we found that the smallest bias was present day, and as well being a medium range in the anomalies comes from the EC Earth 3 model for this region. And then we found that our highest anomalies to cover the spread of possible future changes come from UK ESM, which had the highest future anomaly, and then the MPI, which had the lowest future anomaly. So using this, we're running future prediction scenarios. So we're doing with our 2 end members and as well our ECR3 for our middle member to look at future changes in this region, which I don't have any results of now because this is ongoing, but this is one of the projects that we've been working on. So everything I was talking about before this was using that 1/4 degree regional ocean model, which is a great model because we can run it quite fast and can give us a kind of a balance of speed versus resolution. I'm going to talk now about some of the really high resolution work we are doing, which is not very fast, but can give us some really interesting results. So this here is the highest resolution model over the largest domain that we run. So this is Arc60, so it's Arctic at 1/60th of a degree. So we can see this is the horizontal resolution of this in kilometers. So in the Canadian Arctic in Hudson Bay here, we're looking on a scale of like 500 meters to a kilometer in grid spacing. And this is all the specs from it. We actually currently, I should update this, we now have 1998 as well run, so that's 4 years of model output available for this. It is not fast to run, but I'll show you some really cool, oh, here we go. I'll show you a cool video from it. So this is the surface speed from Arc60 here. And so we can see when you run at this high resolution on the scale, we get really cool coastal eddies forming, and we can see a really good representation of our coastal currents coming down here and through Bering Strait. We can see off the Mackenzie River Delta here, and then some really cool dynamics happening in Hudson Bay as well when you're running at such a high resolution. So we're starting work on this. A lot of this, because this is a kind of one and done run, like we can't run it many times. We can't run a big ensemble on this. A lot of this is process studies that have been working on, looking at things in the Beaufort Gyre and things with sea ice dynamics as well. To run 1 year of this takes around 60 days of real time to get 1 year of output. And 1 year is around 7 terabytes of space take up. So it's a really big run. But it's a really fun project, which we've been working on. So showing something else which is less computationally expected and less crazy on space, but we have been doing to increase resolution though in some of these coastal communities is we worked a lot on agriff nesting. So this is 2-way nesting where we use our ANA4 or ANA4 extended in this case across Bering Strait, 1/4 degree regional domain, and then building nests within this at higher resolutions, which is a much faster way to have higher resolution data and allows us to do fun things with multiple nesting and looking at really specific coastal regions. So this here is our Arc12, which covers the Arctic at 1/12th degree with the background parent nest at 1/4 degree. And this is one project we've been working on with some observationalists out of LAU Fjord here, of looking at building a series of agriff nests at higher resolutions to look at coastal fjord processes. So this here is our overall larger 1/12th degree nest, and then we build down here to off the coast of Greenland here to a 1/60th degree nest, and then going down in the fjord to 1/300th, which gives us a 200-meter grid in order to look at some of these fjord processes, which is a very fun thing that we've just started on. Okay, I might be over time, but that's a big overview of what we've been doing for some of this work, looking at different things with biogeochemistry, improving river runoff, and looking at how we can move forward with future simulations and really high resolution coastal maps. If you have any questions, be to take them out, or my email or anyone's email who worked on some of these projects is under their slide number if you want to contact.
Brilliant. Thanks very much, Taya. That's excellent. Okay, so we have a little while for any discussion now. So I don't see any questions in the Q&A or chat or any hands raised. So I don't know whether Anna, do you have any
Yeah, I had a
questions you'd
question.
like to
I had a
ask either
question
of the
for,
speakers?
yeah, I had a question for Tahia's presentation, and Sarah may want to comment on that, because I've noticed that when you introduce the temperature on the rivers, the heat flux, which I haven't seen done so much in a lot of models, it made a huge difference in the area that there is sea ice. So I was wondering, did you also introduce salinity associated with the rivers? Or did you, okay.
Yeah, so the salinity, we have that in all of our models. We have the salinity, just because it is quite important in the Arctic. But this was where we just started looking at using the heat flux. So the difference still included the salinity between it, the like twin without the heat flux included this.
Sarah, do you want to comment on that? Do you introduce the salinity in your experiments on the rivers?
No, we haven't in these climate runs yet done any of that. But that's really interesting, Taya. So could you just say a little bit more about how you allocate salinity to your rivers? Do you just use a single value for all the rivers, or do you do something different?
Oh, sorry, I just guess I meant by salinity just like it's a freshwater, like a zero salinity that you add like along the coast there. Like not like a low salinity, like a 2 or something like that. It's all 0. So it's a freshwater flux.
Yeah, okay, because I was wondering, like, how you introduce the heat flux if you actually can impose a specific observed salinity, because not all the rivers will have exactly 0 salinity. So if that will have make a difference, but I think that would be interesting too as a future, because I presume that this will affect the sea ice too. Like it will affect the freezing point of the water and things like that.
Yeah. So I guess that's from estuary mixing essentially, and I guess you probably need a separate modelling approach. I know Georgia looks at that kind of thing. Yeah. So
now we can start our discussion, and just to inform the people that they can see it, because it's a little weird how we have you at Zoom. You will be able to participate in the discussion if you want. So if you have a question that you want to discuss with our speakers or something that you want to raise, you can raise your hand, that it's somewhere down there, and I will give you the option to speak. And if you cannot find the hand, just put in the chat, I want to speak, and I will give you the option to be able to hear you, and you'll be able to speak. So to start the discussion, from what I've seen from Sarah's and Tahia's presentation, there is a lot of focus on the ensemble, to be able to have more ensembles of projections, but also sometimes this is very prohibiting, especially when we have really high resolution models. So it would be interesting to comment, like I've seen that, to comment how useful is to carefully choose our ensemble. So for example, as Tahia saw, which models, global models to use as our forcing, and what should be the focus? Should it be as many ensembles as we want, ensembles that we believe, or the best simulation with the highest resolution with just one ensemble? So if Tahia, if you can comment, and then Sarah, if you can comment on that, that would be useful.
Yeah, I mean, I guess like for when you use like the ARC 60 or something as an example, like that's something you can't run as an ensemble just for time and space limitations. We basically can run like 1, maybe 2, of that, depending on how many years you want to run for. But like it's interesting of like using, like we always have focused a lot on resolution and how do you improve those processes as opposed to running as many simulations as you can. That's why we worked on like the GCM selection and stuff of like what is going to be most useful in this
Mm.
case when we're going to run on a multiple ensemble. So looking at like high, low, bias, like that kind of thing, as opposed to just running like 11 different runs with each of the ones and having that large spread. But I think it would depend on like how expensive you are to run.
So Talia, I had a quick question about the GCM selection. Were you looking at a common emission scenario for each of those?
Yeah.
And
This is with, oh, sorry.
No, go on.
Yeah, this is with the SSP 585, so the high emissions scenario in this case for CMIP. I think it's the equivalent to like RCP 8.5 from CMIP 5.
Okay. And did you how did you pick that? Is that
I'm actually not sure how they picked that. That was like, yeah, I know they wanted to do the high emissions probably to look at the like largest possible change.
I guess if people want, if the people are interested in this want a worst case, a worst case scenario for planning, then that's probably a sensible approach. Yeah.
Yeah, so I think a lot of times it depends on what you want to see, because you're going to be able to see more changes and understand maybe the process a little bit easier if you have the worst case scenario rather than small changes that you will not be able to attribute to climate change or just natural variability. Sarah, do you want to comment on the ensembles and selection and things like that?
Yeah, I don't have a lot of experience of that. And it's something we're doing at the moment for Canary. Looking at the impact of the Arctic and North Atlantic on the climate of the European coast, the shelf. So I guess since there we're looking at what the signal is coming down from the Arctic. We're interested in ensemble members that are actually doing a good job in the Arctic. So I guess that would be a criteria that we'd be looking to do there. Yeah, I mean, I suppose it depends how much capacity you've got. I mean, if you can do 2 runs, then you probably want them to be the best you can, the most like present day conditions. If you can do quite a few runs, then sort of doing some of the outliers so that you can sort of capture the entire range of the best circumstances and potentially what the worst circumstances are. We kind of had a lesson from one of the studies that I showed, the one with the circulation of the North Sea shutting down completely. We were able to trace that back to density stratification, something happening in the sort of northern waters in the particular global circulation model we were using. So one way of sort of extending your ensemble, if you like, is by comparing your forcing model with the other global circulation models to see if it's an outlier for models at that scale. So that can be it's not exactly an ensemble, but you're bringing the same sort of thought processes to mind.
So actually, there's a question for you, Sarah, in the Q&A. I don't know whether you can read that.
Okay. How did I build an ensemble of 11 GCMs? Oh, well, I think that is actually a question for Jason, because
I mean, to answer the question very quickly, is we picked the 11 that had data available. So these were CMIP 5, and we were interested in running with ecosystems. So we went for essentially all the models that on the data server that we had, all the models we had that had the requisite ecosystem boundary condition forcing, and that limited us to, I think there might have been 13, and I think some of them didn't quite run. But of the 11, then we didn't do any sort of weighting, certainly not in the paper that Sarah showed. But we did exclude a couple of simulations that had what we call pathologically bad behavior in the present day, and we decided not to accept those. And so the mean was then what was left over, basically, but without any further weighting of those. And I guess it's a point of discussion about whether you should weight or not.
Thank you.
Okay, yeah. Okay, any
I can see in the chat that Yuri put a comment. Yuri,
Aha.
should I allow you to talk and you
Yeah,
can comment on that? I will allow you to talk, and if you don't talk, I will just mute you back. Oh,
Can you hear
yes,
me?
we can hear you.
I don't know if I can open my webcam as well so people can. The comment was mostly picking up on the conversation and the question that you asked between, say, the tension between a large ensemble of a medium resolution model and a small ensemble or single model, as Kaya was saying, for the higher resolution model because of the computational constraint. And something that it would be interesting, and probably things like Flame or these GCO MIP could put as a potential objective would be to see how new statistical tool or machine learning tool could be used to basically represent all the features that the higher resolution model are able to dynamically provide in using a larger ensemble of medium resolution models. So try kind of a statistical downscaling of the dynamical downscale model. Because yeah, I totally agree with Taya that some of these models, especially like the one that she showed, is impossible to run for long period or in large ensemble. But for many questions, that is the type of resolution that is actually needed.
Yes, so that's an idea that like I've seen that a lot of people are keep mentioning it, not only for projections but even for forecast, to use a machine learning technique to either go have a large ensemble and then use a machine learning to go to higher kind of what you want from the higher resolution model, or go the opposite way where you have a high resolution and you use the machine learning to extend your uncertainty and create a larger ensemble. So that's certainly, I think that's where the future, where the whole field is heading, where you try to combine your dynamical model with statistical or machine learning techniques to either extend your ensemble or to take your information on higher or on smaller scales.
And just to chip in there, that there are recently published examples in global climate of kind of coarse resolution climate models being made to behave like high resolution models using machine learning approaches, which is, not been applied in the coastal ocean context, but I think is super exciting as a potential for that. But we have quite a lot of work to do.
So another question that I had, if nobody else has another question about ensembles, was to me, it appears from all the conversations and the presentations that we had for this session that one of the most important things in the coast, if we want to have if we want to have any future correct projections that can give us something that we can provide to policymakers, one of the most important things is the land-ocean interaction, and we have to capture that correctly. So I've seen that there is a large effort to include rivers and everything that goes with the rivers, not just fresh water, nutrients and things like that. And Sarah mentioned that, this is where people live, so there is going to be pollution. So is these projections, do they include this pollution? Are there scenarios of how this anthropogenic activity, not that is directly linked to climate, is included in the river outflows?
Yeah, there are land surface models that do land use scenarios, do different scenarios of population density and things like that, which some of these are global, some of them are regional, but it's a different community to us, and I think one one important thing is actually to be able to connect up the community so that the importance of that type of modelling within the coastal ocean is reflected, and we kind of have a better dialogue and better information there, because at the moment it's kind of quite arm's length. Yeah, we take data from data sets or papers. You know, we're lucky enough to have hydrological modelers who are friends, and we can do kind of co-projects with it. But it's more usual to kind of be kind of working a bit remote control on that. Yeah, but I agree. I think it is a real key aspect for the future. Yeah.
Yeah, I think. Yeah, Sarah, go ahead, please.
No, I was just going to say, yeah, we have sort of in the past been lucky enough to work with hydrological modelers, and you know, hopefully we will again in the future. One of the issues can be regions that they're studying. It cannot. Sometimes it doesn't cover the whole of your regional model. That can be a difficulty, and then trying to get a consistent data set. You've got very good data in one area, but not in another area. So it's encouraging for sort of the freshwater inputs, but the biogeochemical stuff is sort of another subject altogether. I mean, there are fantastic modelling efforts going on. One of the recent ones, the International Nitrogen Assessment. You know, they're doing sort of projections of land use changes and how that impacts on nitrogen coming into the ocean. But for running your ocean ecosystem model, you need more than nitrogen. You need other things as well, other nutrients, oxygen, sediments, and other things as well. So it sort of requires quite a lot of joining up, I think, to get a complete set of future land influence data to actually put into your coastal ocean model.
Thank you, Sarah. Yeah, it seems to me that we don't even have temperature yet, so it is difficult, but I think that's a problem that needs to be tackled if we are to do any useful future projections very close to the coast. And yeah, are there any questions for the participants about this land-ocean interaction and rivers? Please, if you have a question or a comment, put it in the chat. And if you're shy to speak, you don't have to speak. I can read your comment. Oh, another issue that it hasn't been highlighted a lot, but I've seen it in Tahia's talk, was about the coupling with waves, which usually is ignored entirely. I don't think there is any global climate projections with wave coupling, like 3D ocean wave. Maybe I'm wrong, but I don't. So, but I think that it starts becoming very important to include waves if we are to do any useful projections, especially for saying to people where it's going to become problematic in terms of sea level changes. So any comment to that by Tahia or Jason or Sarah?
I don't think I'm not aware of any I know there are global future wave projections, but not any interactively coupled that I'm aware of.
Yeah, so I think that
but I haven't looked. I have to say there might be somewhere.
I was going to say same. I'm not sure either if they have like global, because we've ran this for just we've only run not the future projections yet, but the Finecast work. And we just ran that for the marine conservation area itself. Specifically for Jones Sound was the point for it. So I'm not sure if it's been done on a larger scale yet. And I know this is the first time we've run Wave Watch 3. So this is our first going through wave modeling.
Yeah, I'm not sure even regionally I'm sure that there are studies doing wave watch maybe with atmosphere or separate, but have like a fully 3D model with wave watch. I don't know how many studies there are out there. Sarah, yeah, I'm not sure. I know that, yeah. So that's something that maybe we should be aiming at least for shorter term projections, because this is when people care, like what is going to happen if I live near the coast in 20 years? Should I be moving like away from the coast or things like that? Okay, great. So I think that's most of the discussions that most of the questions that I had. I don't know if any of you want to raise any other issue that you think is important.
I think I'm good for now.
Just to highlight then, before we conclude our discussion, that there is this document where I will put again in the chat the link. So this document is about for us to be able to understand what will be needed in order to set this coastal ocean model intercomparison program. What you think is important? We have some questions there, and I will leave this document open for the whole day today and tomorrow. So if you have some time just to put any thoughts you have, you can put it anonymously. So put whatever you want, even if it's cruel, and we'll look at it and try to make sense of what the community thinks they need and what it will be better for us to be able to put this intercomparison program together.
Okay, thanks, Anna. I've got one last slide, so I will share my screen before we draw this to a conclusion. So, and this is, let's jump to the end. This is basically to highlight another activity that's going on in this space. And so this is coming out of the World Climate Research Programme and the Clyde Ocean Model Development Panel within that. And that group has teamed up with Cordex, so the people responsible for coordinating largely atmospheric climate downscaling, to develop a vision for regional future climate projections and take a coordinated view. So very aligned with what we're doing in the context of the UN decade, and we'll work very closely with this activity. But I just want to point this out as it will probably reach out to a very similar community to Flame. So Angelique Mellet from Equator Ocean International in France, and is pushing this forward. So I just wanted to point this one out. And the last thing to say is that the door is very much open in Flame for anyone else who is interested in participating. I put up a QR code about Flame there to get more information, and one about Coast Predict, or if you do want to know anything more or want to get involved, then just drop myself or Anna an email. So I think we'll stop there. We'll say thank you very much. Good morning, afternoon, evening, whatever time it happens to be where you are, and have a brilliant rest of your day. And I'd also like to say thank you very much for Taya and Sarah for your brilliant presentation. That was really great today. So thanks very much, everyone.